In this lecture, we start to tie the pieces together and formulate our column generation approach. Remember the tools that we have in hand. We have our dancing wolf reformulation of an integer program. We call this the master problem. We saw that in the master problem, we can decompose the problem into a set of columns. We also saw that we can look at the dual problem. It was critical that in our master problem, we were looking at a linear program, so that the linear program optimal is equal to the dual optimal. We also saw that we could solve the linear program master problem on a restricted set of columns. We denoted this restricted set of columns by C tilde, A tilde, and E tilde. The general overview of our column generation technique is that we're going to solve the restricted linear program master problem with these tilted quantities. Associated with this linear program master solution is going to be a dual solution. This is the dual solution to our restricted linear program master. We denote this by putting a tilde on the pi and the mu. After we have this pi and this mu in hand, we check to see if this dual solution is a feasible solution to the full dual program. The full dual is associated with the original linear program master, including all of the columns. If our dual solution to the restricted linear program solution happens to be feasible for the full dual problem, then we stop. This is because at this point we know that we have an optimal solution. It's easy to see that we have an optimal solution in this case. First, we know that our linear program master problem, solved on the restricted set of columns, is a feasible solution to the original linear program master, with all the columns. Now that we know our dual solution is a feasible solution to our original dual problem, we know that this solution is actually optimal because our dual solution meets the linear program optimal solution. However, if we find that our restricted dual solution isn't feasible for the full dual solution, we don't stop the algorithm and instead we add a particular column. The key to the column generation algorithm is this step, adding a column, and throughout this lecture we're going to focus on exactly this step. Once we have stopped and hit our stopping criterion, we have a feasible linear program solution. This is the linear program master solution though, and so our variables are written in terms of lambdas. And we're going to call these the lambda tildes since they come from a restricted linear program. To recover our original solution, we have to actually find the values for x. In this case, we use our original equation, the equation we used in the initial substitution for the Dantzig-Wolff decomposition, or reformulation, to find our x's. In particular, the x's are written as the sum over all the feasible solutions in capital Xi multiplied by the lambda i's. In effect, we've taken the convex combination of the feasible solutions associated with this particular lambda. This turns out to be an optimal solution to our original linear program before our reformulation. Before we look at how we're going to add columns to our program, we're first going to recollect some of our notation. First, recall that we have Z tilde LPM. This is the restricted linear program master solution. In this linear program, we have the tilted versions of all of our quantities. We also have a set of columns. There's one column associated with each variable. In this case, the variables are the lambdas. Each lambda is associated with a particular feasible solution, and so our column is associated with a particular feasible solution. The feasible solution in question is the variable x inside of our column. Finally, we have a dual vector, pi mu. This dual vector is the dual vector to our original linear program master, including all of the columns. There's also going to be an associated dual vector for the restricted linear program master. We'll denote this by putting a tilde on top of the pi and the mu. To solve the linear program master solution, we're going to look at the idea of having a lower bound and an upper bound. Our lower bound comes from solving the restricted linear program master solution. Our upper bound is rather questionable though. And before we actually develop an upper bound, we're going to look at the column generation approach. The idea of our upper bound, and in particular, the idea of how we're going to add columns, comes from looking at the dual of our linear program master solution. Here we've written the dual. Note that the objective function of our dual is b times pi plus mu. There's only one type of constraints associated with our dual. The constraint is pi times a plus mu times e is greater than or equal to c. Just notationally, pi times a is the same as writing a transpose times pi, which is possibly more familiar if you've written duals before. In this case, we have our dual written in a compact vector notation. But to work with the dual, it's actually easier to expand this vector notation. To expand this vector notation, we expand first the matrix A into a block matrix form. Each one of these blocks is associated with a particular part of our decomposition, capital Xi. We write A as A1 times X through AK times X. Note here that we've explicitly modeled the variable X. X here is associated with a feasible solution in capital Xi. We do the same thing for our cost vector C. C is now written as C1 times X through CK times X. We also do the same thing for U, part of our dual solution. In this case, we write U as U1 through UK. In this case, U1 through UK are all real variables, as opposed to the other forms where we have vectors in a block matrix format. Now we can expand our vector notation. We keep the objective the same, noting that U is actually a vector of U1 through UK. What we're expanding, though, is our constraint, and our constraint is expanded according to the decomposition. In this case, each portion, or each part of this constraint, is associated with a particular part of our decomposition. So we can write pi times lambda ix plus mu I is greater than or equal to cix. And we can write this for every part of our decomposition I. Note that inside of this constraint, even though we've written it for our decomposition, we have this lingering variable x. This x is actually a constant, and that constant is associated with a feasible solution in capital Xi. In total, what we've done is we've written our dual by writing the same objective function and expanding our constraints so that we have one constraint for every part of our decomposition. We're still going to defer developing an upper bound and instead talk about an optimality check. Usually, we stop and conclude that our solution is optimal when we have an upper bound that's equal to our lower bound. In this case, we're going to stop in a different criteria. Although this is eventually going to be identical to stopping when an upper bound is equal to a lower bound, it's easier to think about this as stopping when we have a dual feasible solution. Recall that when we were just talking about the dual, we were talking about the dual to the original linear program master problem. This is the dual when all the columns are included. There's also an associated dual whenever we have a restricted set of columns. This restricted dual is pi tilde mu tilde. We can put pi tilde and mu tilde into a restricted dual, and we know that this is going to be a feasible solution to this restricted dual. What we're interested in, though, is whether this pi tilde and this mu tilde is going to be feasible to the unrestricted dual. One way to check whether this dual solution is feasible to our original dual is to check each constraint individually. Note that this is going to be computationally intractable, though. In our linear program master problem, there's an enormous number of variables. For each one of those variables, we're going to have one constraint in the dual. So the dual is going to have an enormous number of constraints. Instead, what we're going to do is we're going to check all of these constraints for a particular part of our decomposition implicitly by solving an optimization problem. Specifically, we're going to find the quantity delta I. Delta I is going to look over all the feasible solutions in Xi and find the largest amount of violation any constraint can have restricted to this set of the decomposition, this part of the decomposition, I. If we find that delta I is less than or equal to 0, we can conclude that all constraints associated with this part of the decomposition are going to be satisfied. And if we can conclude that delta I is less than or equal to 0 for all I, then we can conclude that our dual solution for our restricted dual is actually going to be feasible for our unrestricted dual. Once we know that this is a feasible dual solution to our original dual, we can conclude that pi tilde is optimal to the original master linear program. And now it's worthwhile to think about exactly why this is going to be true. We have our solution z tilde LPM. Because of duality theory, we know that this is exactly equal to our restricted dual, which we're going to denote by dual tilde. Now that we've shown that this dual feasible solution to the restricted problem is feasible to the original problem, we can conclude that dual tilde is equal to dual, where dual is the dual solution to the unrestricted problem. Now we know again from duality theory that this dual is equal to ZLPM. By chaining these equalities together, we can conclude that Z tilde LPM is actually equal to ZLPM, our optimal solution in question. Now we ask the corresponding question of what happens if we find that our dual is infeasible, and in particular that our master dual, the unrestricted one, is infeasible. In this case, we found our delta I, and delta I is found by maximizing over all feasible solutions in capital Xi of the amount of violation in our dual. If we find that delta I is greater than 0 for some I, then we can conclude that there's a constraint that's violated in our master dual problem. In effect, this is solving a separation problem. We have a dual problem, we know that it's infeasible, and we've found some constraint that's going to be violated. In this case, the constraint that's violated is the one that's associated with the maximum. In this case, we're not so interested in the actual dual, though. We're interested in the original linear program master. So by finding this constraint that's violated with our separation problem, instead of adding a constraint to the dual, we're going to add a column to our original linear program. Because of this, we call this subproblem, solving this max over all xi, the column generation subproblem. This is in fact a separation problem. It finds a violated constraint. But because of the context we're in, instead of adding this constraint, we add a column. So now our column generation is simple. We find delta I for all the i's, and include the constraint that maximizes these delta i's. After we include this constraint, we resolve our problem and iterate. Now we can see why expanding this to a large number of variables is useful. By expanding to a large number of variables and iteratively adding columns, we have an iterative procedure to solve a linear program. Whenever we can stop with a restricted linear program that only has a subset of the columns and not the full set of columns. And so in theory, we can do less computational work. Although occasionally, it might be that we need to add a large number of columns anyway, in which case our solution strategy, although computationally intractable, could provide a heuristic to actually solving our original linear program.